Continuing on with our discussion of concentration units, we're going to talk about molarity. So molarity is the concentration. It's used at capital M. It's the number of moles of solute dissolved in 1 liter of solution. So just like we saw previously, concentration unit, it's going to be a ratio. It's going to be moles of solute, that's an amount of solute, over your amount of solution, volume of solution. We don't use a 100. It's not a percentage here. It's not a parts per or anything like that, but just moles of solute per volume of solution, where that is in liters. So molarity is the most common unit in chemistry for concentration. When we talk about this, if we talk about a value, it's a molar quantity. So instead of saying like, you could say the molarity is 3, but you would also just say 3 molar for a concentration, just like you would say like 3%. That's how you describe that unit. But capital M is that what we have there. You will note when we're talking about the volume of solution, it does need to be liters. It can't just be any volume that we want. It can't be milliliters. It can't be gallons. It can't be anything else. It has to be liters. Molarity is a made-up unit. This has no real natural or physical basis, and so we've just decided it's going to be volume in liters. The reason why we choose liters is that it gives reasonable numbers. So why do we use molarity in chemistry? Well, the real reason is because when we're talking about chemistry, we care about the number of molecules, right? We care about the number of molecules or atoms or ions or whatever that are present for doing chemical reactions. And so for a given molarity, say 2 molar, you are guaranteed to have the same number of molecules for a given volume. So for example, I could have 4 molecules. If this, whatever molarity this is, I could have 4 molecules of my orange, 4 molecules of my blue, or 4 molecules of my red and yellow. Whatever it is, it doesn't matter what the compound is. It doesn't matter how big the molecules are, how many, if they're ions, if they're molecules, if they're atoms, the concentration at a certain molarity, we have the same number of particles floating around in solution. For a given solute, for example, the blue solution, if I do have a higher molarity, I'm dealing with a higher number of molecules. So, for a given solution or a given solute, it still works in the same way as normal molarities, but really that top row is why we use molarity in the context of a chemistry, because we care about the number of solutes. Generally, we make solutions to do chemistry, which is doing reactions. We care about the number of molecules because that's how chemistry happens, by number. All right, 400 milliliter solution contains 56.3 grams of sulfuric acid, which is H2SO4. What is the molarity of the solution? This is a very common problem. You have made a solution. It's a 400 milliliter solution. You put 56.3 grams of sulfuric acid in there. What's the molarity? You want to characterize a solution you made. You want to know the concentration. What's the molarity?
All right, we want to know what is the molarity of the solution. And again, molarity is a concentration unit. We really want to be mindful, if we just know the names of the concentration units, we're always going to be able to come up with the fact there's an equation. Molarity is equal to moles of solute divided by liters of solution. And so if we have those values, we could plug them in. When we're looking at this, when we're faced with this, 400 milliliter solution contains 56.3 grams sulfuric acid. We want to think about, again, what's the solute, what's the solvent? When we talk about a solution containing something, the sulfuric acid, that almost always implies it's the solute. And especially because if you think of 400 milliliters, this is this is going to be a decent amount of stuff. 56.3 grams, not that much stuff, so likely the solute because it's a lower amount. And so in this case, we know that basically we'd be looking for, we could rewrite this as this is really going to be moles of H2SO4 per liter of solution. So do we have each of those? Almost, but not quite. Moles of H2SO4, I don't have. I have 56.3 grams sulfuric acid. Liters of solution, I don't have. I have a volume, but it's 400 milliliters. So this is a very, very common situation. When we make a solution in the lab, we want the concentration in molarity. That's our most useful description. But we don't normally measure amounts of stuff in moles, and we don't normally measure solution by the liter. 400 liters is already quite a large volume for the laboratory setting, but we are almost always measuring in milliliters, and we always measure our solute masses in grams. So it's very common to have grams for the solute and milliliters for the volume. So when you're computing molarity of a solution that you've made, you almost always, need to do a conversion step beforehand, where that conversion step is taking the grams into moles and taking the milliliters into liters. So we'll go ahead and do that metric conversion first. 400 milliliters times, we know that there are 1,000 milliliters per 1 liter. And that gives me 0.400 liters. So I can convert my given units into the desired units. Molarity always needs to have that volume in liters, so switch from milliliters to liters. I also want to take my 56.3 grams H2SO4 and multiply that by the molar mass. The molar mass for H2SO4 is 98.08 grams H2SO4 in 1 mole H2SO4. Molar mass, you can compute it using those values in the periodic table, adding them up, or you can also just look up the molar mass of sulfuric acid. We do need to use it though, and it becomes 0.574 moles of H2SO4. Now that we have our target units, we can plug them all back in. Molarity is equal to 0.574 moles of H2SO4 divided by 0.400 liters. That gives us 1.44. The units we would see, it's this moles H2SO4 per liter. But that unit right there, that whole thing, that's moles per liter, that whole thing is just molarity. That is my capital M. So my answer is 1.44 molar. And normally we would write the solute after that. So we would say that this solution is 1.44 molar H2SO4 sulfuric acid. So we're giving information on the concentration, and we do normally write out or say the solute in there, because that's what's relevant. You got 1.44 molar of that. And so this is very common when you've made a solution. You have some mass that you've dissolved and some usually milliliters of volume or anything. It's very uncommon to measure mass volume out by the liter. That's just really big and in a lab setting. And so normally it's in some other unit, maybe ounces, quarts, pints, whatever it is. Convert that to liters, because the equation for molarity always has liters of solution on the bottom, not just volume, but specifically liters.
Participation 125, question 1. How much potassium hydroxide is required to make 2.5 liters of 0.10 molar solution? This is the first question on participation 125, due Tuesday, January 25th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how much potassium hydroxide is required to make 2.5 liters of 0.10 molar solution? So this is looking for a calculation. We just need the number. You don't have to show work for your calculation. You want to turn it in, that's fine. But I'm looking for the number. How much potassium hydroxide? All right. First participation question down. Look at that. Second video, already got a participation question. See you in the next one.